So we left off yesterday right before example 4. And example 4 is hopefully going to start to bridge the gap into explaining the application of these sums, these areas under the curve, and how they apply to broader areas of mathematics and science. So suppose that the odometer on your car is broken and we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds and record them in the following table. Now, the first thing we should probably notice is the units on this table. The time is given in seconds. The velocity is given in miles per hour. So those units do not agree. We can't just multiply time in seconds by speed in miles per hour and expect to come out with an accurate reading. So the first thing we need to do is convert one of them. Now we could convert the time to hours in just a couple steps and it'd be pretty easy, but we'd be dealing with some really small numbers and end up with kind of ugly approximations. The better option, I think, is to convert the velocity. Now, instead of converting from miles per hour to miles per second, which would give us, again, really, really small numbers, I think the most appropriate thing to do is to convert to feet per second. Now, I'm going to trust that is something you all know how to do. The lesson here is not in how to do it, but in recognizing that it needs to be done by evaluating the units. So that's something you definitely have to pay attention to in your homework and on the test. Make sure that your units agree, otherwise you're not going to come to the right solution. So if we convert the velocity in miles per hour to velocity in feet per second, we get these numbers here. Yeah, let me use a different color so it's easier to see. So what we want to do is use our estimates, our specific measurements of our speed at any given time to estimate the total distance traveled. Now, we can approach this two ways. The first way is to kind of operate under the assumption that for the first 5 seconds, you're running at roughly 25 feet per second. For the next 5 seconds, you're running at roughly 31 feet per second, and then 35. And so what we could do is we could say, for the first 5 seconds, I travel for 5 seconds at 25 feet per second. And so I get 125 feet. And then for the next 5 seconds, I travel at 31 feet per second, and I get 155 feet. And I could do this at each individual step, but I have to be careful not to use too many. So, for instance, here's I've traveled for 30 seconds. Here's my first 5, second, third, fourth. Okay. The next 5 is at 32. The next 5 is at 46. Now, notice what I have here. I have 6 intervals of 5 seconds apiece. That's 30 seconds. So since I'm leaning towards the left-hand side of this, and for the first 5 seconds taking 25, okay, I'm leaning to the left as we go along. And so what I don't catch is that 41. Okay. So maybe the more accurate way to write these marks, to tick these off, is to say for the first 5 seconds I did 25. Up to 10 I did 31, and so on. And so we see that 30 end right about here. And when we add those all up, okay, the arithmetic is fairly easy. We get 1,135 feet. So that's one approach we could take. The other approach we could take is more of an overestimate. And it says for the first 5 seconds, I'm running a roughly 31 feet per second. And then for the next 5, roughly 35 and 43 and 47 and 46 and 41. So basically, you have two options. And that is to either use the speed at the beginning of your 5-second interval or the speed at the end of the 5-second interval. And you get either right or left-hand sums. Okay, so in this case, we're going this way. And when we sum those all up, we get a total of 1,215 feet. So we have an overestimate and an underestimate. And the best we could say is that our actual distance is most likely somewhere in between those two numbers. So basically what we've done is we've taken and found the area underneath our displacement curve. So if we looked at a graph, say a bar graph, or a histogram more like, it's actually neither, it's just a simple displacement curve, but then broken up into bars, we're taking the area under each. Okay, so in this one, this is where we're taking the left-hand side, the speed at the left-hand end. Okay. And there we go. And so the area under the displacement curve, the area under the velocity curve, this is velocity. The area under it is displacement. Now, there's a reason, I think I said distance a couple of times. There's a reason that displacement is more accurate. Theoretically, my velocity function could dip below the x-axis if I were traveling in a negative direction. So say east was positive and west was negative, then I could say that traveling west would give me a negative velocity. In which case, my area, which would include this region here and this region here, would be my total displacement, how far I am from where I started. Not my distance, which is how far I've traveled. Okay? So the displacement is how far you are from where you started. The distance is how far you've traveled. So this is just another application of areas underneath the curve. Any questions? All right, so let's jump into 5.2. We're going to take a look at the definite integral. Here's where it's going to start to. We're going to start a little bit with sums and how the integral is defined by the Riemannian sum. And then as the section goes on, we're going to translate that into more basic arithmetic. If f is a function defined for a is less than or equal to x is less than or equal to b, we divide the interval, the closed interval, from a to b into n subintervals of equal width, with delta x, that is that width, being b minus a over n. So we're taking the length of the interval by subtracting the endpoints and dividing it into n subintervals. We let x naught, which is equal to a, x1, x2, and so on up to xn, which is equal to b, so your beginning and ending points, be the endpoints of these subintervals. And we let x1 star, x2 star, and all the way up to x sub n star be any sample points in these intervals, so that x sub I lies in the ith subinterval. Okay? So x sub 2 star is some sample point in between x sub 1 and x sub 2. Then, the definite integral of f from a to b is written as such. So this is the integral symbol there. And we would read this as the integral from a to b of f of x is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I star times delta x, provided that this limit exists. If it does exist, we say that f is integrable on the closed interval from a to b. Now, yesterday what we were saying was, or it wasn't even yesterday, it was Thursday, we were saying that this limit would always exist. Well, the condition for it to always exist was given in the definition of that sum when we said that f was continuous. Now we're looking at a function that may or may not be continuous. Okay? And so those two concepts are going to work together, whether or not it's continuous and whether it's integrable. Okay? So that integral sign is basically an elongated S, stands for sum. F of x is called the integrand. Okay, that's what we're taking the integral of. And a and b are called the limits of integration, the lower limit and the upper limit. And so this process is called integration. Now, let me tie this back to the last problem that we did. When we calculated the displacement using the area under the curve, taking those various sums, our lower and upper sums were about 80 feet apart. Okay, one was 1135, the other was 1215. Because we took measurements of the velocity every 5 seconds, how could we get a more accurate estimate of what our actual displacement was? Let's take it back. We had a table, velocity given every 5 seconds. And we found a displacement to a certain degree of accuracy. How could we make our estimate more accurate if we're driving that car? What would we have to do to make our estimate of the distance traveled more accurate? We could record our speed more often. We're only recording our speed every 5 seconds. Okay, if the speed varies greatly in between those two time frames, then your displacement changes significantly. So in order to get a more accurate estimate, we want to take more frequent measurements. The same principle applies in these type of problems. That's why we take the limit as n approaches infinity. When we increase the number of subintervals, we increase the accuracy of our estimation of the area under the curve. We're taking more and more subdivisions, and so the top of our rectangles approaches the actual curve more closely. Okay? If we only take a couple, we end up with huge gaps or huge overlaps, depending on which end we're on. So let's start to look at how this is worked out. Yeah, I don't think I want to write anything in there. If f is, it should say either is, it should just say is continuous. I guess you could write a continuous function. So I stopped mid-thought there. But if f is continuous on AB, or if f has only a finite number of jump discontinuities, then f is integrable on AB. That is, the definite integral exists. So in order to understand that, we have to remember what a jump discontinuity is. Now, I would ask for one of you to recall it, but it's kind of hard to describe. Remember that a jump discontinuity in a graph is when you have a function that jumps from one point to another. Okay, so maybe it's something that looks like this. Okay, that's a jump discontinuity, provided that those are both at the same x value. And so what this theorem is saying is that if f is either continuous or the number of jump discontinuities is finite. Okay. So most of the functions that we've dealt with fit this description. Not so much the jump discontinuity part, but the continuous functions. The only ones that we deal with that might have jump discontinuities are piecewise functions. But polynomials, exponential functions, trigonometric functions, logarithmic functions, all continuous on, well, not quite on a closed interval, but on open intervals, and we could close them off to make certain areas continuous, which is what we'll end up doing for a lot of our integrals. The next statement made here says that if f is integrable on ab, then the integral from a to b of f of x dx is equal to the limit as n approaches infinity of I equals 1 to n of f of x sub I delta x. So what this is saying, well, what's the big difference between this statement here and this definition right here? There's one little symbol that changes the two. The star. Notice that on the limit here, we have f of x sub I star, which tells us we're taking sample points, any random point inside that interval. The difference here is that we don't have that star. So instead of taking sample points, we're taking endpoints of the intervals. And this theorem states that if you take endpoints of the intervals, you still get an accurate sum. Now, to a certain degree, that ought to make sense. We're not going to go through the proof of it, but that x sub I was a randomly chosen sample point in an interval, so why can't it be chosen to be an endpoint? That's basically the statement that's being made. So the first thing we're going to do is we're going to learn how to express this sum as an integral. That's the first step to understanding how to calculate an integral. And we want this as an integral on the interval 0 to pi. So the first thing we should write is that we're taking the integral from 0 to pi. That's the limits of our integration. All right. The other things that need to go in here, we need to determine what f of x is. And then I'll give you a little secret. There's always going to be a dx there, or d whatever your independent variable is. Okay, sometimes you'll have a function of t or of u or whatever, and so you'd have dt or du. But it's d of whatever your independent variable is. And by the way, that dx is basically an analog of this delta x. It's that it represents... Okay, so as I was saying, this dx here and that delta x are essentially the same thing. Dx is that derivative, that differential change in x, and delta x is the width of each interval, so they're tied closely together. The only thing we have left to really interpret is what is this doing as a function? Well, it's consistently plugging your endpoints into a cube, and then it's multiplying your endpoint x by sine of that same endpoint. So that's what our function should look like. So all we have to do is plug that into our integral. And that's all it takes right there. Identifying what the function is, determining the limits, and writing it in the proper notation. Okay? This right here isn't part of the notation. That's just what I was using as a filler. Any questions on that? All right. So we're going to start by evaluating integrals using their sum equivalents, and we're going to kind of hopefully transition into, hey, welcome.
Thanks for the fiesta.
Yeah, it was my fault.
I'm just kidding.